So the first step in naive Bayes is to learn the probabilities of the model from the training data. How do we do that? The jar of jelly beans here represents our training data. Let's say we have a classifier with two classes, good jelly beans and bad jelly beans. We pick one jelly bean at a time, or one training example at a time, from the jar. We add 1 to the count corresponding to the training label of that jelly bean. So if this jelly bean was labeled good, we add 1 to the count of good jelly beans. We also look at the features of the jelly beans. Let's say that we have one feature here, the color of the jelly bean. So when we pick a good red jelly bean, we add 1 to the count of red jelly beans given good jelly beans. When we pick a bad red jelly bean, we add 1 to the count of red given bad. The thing to keep in mind here is that this jar is only a sample. We are estimating the distribution of jelly beans based on this limited sample. Our goal here is to estimate the distribution of a random variable from a limited sample. A random variable may be a class or a feature. We do that empirically using our training data. For each class, we look at the empirical rate of that class. We count the total number of examples with that label, and we divide by the total number of training examples that we have. This is the maximum likelihood estimate of the label. We do the same for the probability of each feature given the label. We count the total number of examples from that class with that feature, and we divide by the total number of examples from that class. So let's say we have 3 examples, 2 red ones and 1 yellow one. To calculate the maximum likelihood probability of red, we count 2 red examples, that's our count, and we divide by the total number of examples we have. So it's 2 over 3. This is the maximum likelihood estimate of red calculated from this sample. For our digit recognition classifier, the first thing we need to learn from the data is the distribution over the digits. We don't have a uniform distribution here. You can see that 1 is the most likely digit, 4 is the least likely. So the distribution will depend on the domain. A distribution of digits in zip codes will be different than the distribution of digits in phone numbers. So we learned the distribution that is reflected in our training data. So here's a training example. It's labeled as a 3. When we examine it during our training phase, we add 1 to the total count of 3s. So it contributes to this P of 3 here. P of 3 is actually the total count of examples that are labeled 3 over the total number of training examples. This training example also contributes to the probability count of all the features given a label of 3. Each pixel here is a feature, so for each pixel we have a conditional probability table, a CPT. So this training example will contribute, for instance, to P of F55. This is the probability of this pixel here being on given a label of 3. And this probability is equal to the total count of images of 3 that have this pixel on divided by the total count of 3s in our training data. Before we move on to the spam classifier example, I want to introduce a simplifying representation that we often use in natural language processing. It's called the bag of words model. In this model, a text or an email is represented as an unordered collection of its words, a bag of words. Grammar is ignored. So two text documents will have the same representation if they contain the same words, even if the order of these words is not the same. Our spam classifier is based on the bag of words representation. Our features in this specific example are only the words in the email. We're not going to use any other feature like whether or not the sender is in our contacts. We won't use all caps or dollar signs here. We're just focusing on the words in the email. And remember, we are ignoring the order and we are ignoring the grammar. So from our training data, we compute P of spam and P of ham. These are called our priors. Let's say out of all our training examples, 2/3 of them are ham messages and 1/3 are spam. So we compute P of ham as 0.66 and P of spam as 0.33. We also compute the conditional probability of each word. So P of the in a spam message is 0.0156, whereas in a ham message, its probability is slightly more. So all these probabilities are based on our training data set. Once we have these probabilities, we are ready to classify new unseen email messages. Let's see how to classify a new email message with our model. So initially, before we even read the message, we have our prior probabilities. We know that 1/3 of the messages are spam and 2/3 are ham. So without looking at any word, there is a 66% chance that our message is ham. So this is our prior. This is the probability of the parent. This is the probability of the label. Let's read the first word in this message. And let's say the first word is Gary. Now, for some reason, Gary is much more likely to appear in a ham message than a spam message. It's 10 times more likely to appear in a ham message than a spam message. And that these probabilities were based on our training data, remember. So now how do we compute the probability that the message is spam, given that it contains Gary? We haven't looked at the other words yet. We just looked at Gary. So we apply what we know about probabilistic reasoning. Remember, we have a Bayes net here, and we know how to apply probabilistic reasoning to our Bayes net. We know how to conduct probabilistic inference. So what do we have here? We want to calculate the probability of spam given that we have seen Gary. This is our evidence. The word Gary is our evidence. It's also a feature, right? So we want to calculate P of spam given Gary. So this is equal to the joint probability of spam and Gary divided by probability of Gary. But the probability of P spam and Gary is given by P spam times P Gary given spam. Remember, we have a Bayes net here. All right, so P spam is our prior probability of spam, that's 0.33. P of Gary given spam is also given to us by the model, it's 0.00002. We don't have P of Gary at this point, but we know how to compute it, or we know how to normalize so that we don't need to compute it. So the second step we need to do here is compute P of ham given Gary. So we do something similar here. It's equal to this. And we have P of ham, and we also have P of Gary given ham. So now this is P of spam given Gary, and this is P of ham given Gary. Since the message can only be ham or spam, these two have to add up to 1. So we can either normalize or we can compute P of Gary. Let's go the normalization route and do this. So the total here, we add this, and then we divide both quantities by z. So we get this number here, P of spam given Gary is 0.05, and P of ham given Gary is 0.95. So just by seeing this first word here, Gary, ham wins, right? Ham is much more likely right now, or so far. We proceed to read the second word in the message, and the second word is would. And here, this word also favors ham messages. So after reading this word, we compute the probabilities just like we did here, except now that instead of our prior probability 0.33, we use the probability from the previous step. So this is similar to what we did in our homework. We just computed the probability step by step, and at each step we used our prior, which was the probability computed so far. So you can see here that what's really important is not the absolute value of these numbers here. What's important is basically the ratio of these two numbers. How much more likely is it to find this word in ham versus spam? So Gary and Wood both tipped the balance in favor of ham. So now we read the next word, and the next word is you. Now for this word, P of U given spam is higher than P of U given ham. We have 0.008 here, 0.003. So when we carry out our computation, we tip the balance in favor of spam here. The total probability of spam now increases to 0.1 and ham decreases. So here again, it's the ratio that counts. Let's say the next word is like. Like is almost neutral, slightly more likely in spam. So we have a slight boost to spam here. Then we have 2. No big changes here. These two numbers are similar. Lose. Now lose is 4 times more likely to be found in a spam message. So lose will favor spam. So our probability of spam now is increasing, ham is decreasing. Wait is 8 times more likely to be found in a spam message. So after reading wait, our probability of spam now is up to 81%. And then we can continue here. And by the time we're here, by the time we have read all the words in the message, we can see that our probability of spam, given the words we have so far, so this is given all the words we have read so far, is 99%. So we're ready to classify this message as spam, and we won't be wrong.